Hello, ladies and gentlemen. Welcome to my simple simulation that simulates collisions. Now, what is simulation? Well, I really like computers and how perfect they are. They can calculate vast numbers of equations very precisely. I also like programming. I plan to get a job in the computer science field. Also, it's free and there's an undo button for my mistakes. So, today you will learn all about collisions, how momentum is conserved, and how to calculate final velocity after collisions. No, no, all collisions here are perfectly elastic. There is no friction or air drag, and collisions will bounce off the wall perfectly. Right? Let's see the simulation in action. Beautiful, wasn't it? We just saw that a ball of mass 2 kilograms and velocity 3 meters per second hits a ball of mass 1 that's standing still. After the collision, the first ball has a velocity of 1 meters per second, and the second ball has a velocity of 4 meters per second. And the question is, was momentum conserved? Momentum must momentum before collision must equal to momentum after the collision. Momentum is calculated by mass times velocity. So we plug the numbers in. We can plug in 0 for the second ball because it was standing still. And after doing some quick math, you see that 6 is equal to 6. So yes, momentum was conserved in the simulation, which means it was working perfectly. Now, let's get into something a little bit more difficult. We can see here that a ball of mass 3 and velocity is 4 is going to hit a ball of mass 1 that's staying still. Now, what will be the final velocity of these balls after the collision? And how do we even calculate it? We have to use two simple physics laws: the conservation of momentum and conservation of kinetic energy. We already went how to calculate conservation of momentum. So, how do we calculate kinetic energy? Kinetic energy before the collision must equal to kinetic energy after the collision. Ki is equal to Kf. How do you calculate kinetic energy? Kinetic energy is 1 half mass times velocity squared. We add up the kinetic energy of both balls before collision, then compare it to both balls after collision. As before in the last simulation, since the second ball was standing still, we can plug in a 0 in that space. After plugging in the numbers, we get these two equations. We can simplify this further to get this. As we have two different variables in two different equations, which is a system of equations. Now, for the sake of time, I won't be going over through the math, but just so you know, it should be simple to understand how to get the answer. So, the answer is the final velocity of the first ball should be equal to 2 meters per second, and the final velocity of the second ball should be equal to 6 meters per second. Or the final velocity of the first ball is equal to 6 meters per second, and the final velocity of the second ball is equal to 2 meters per second. Well, how is that possible? Well, if we go back, you can see that final velocity 1 in the kinetic energy equations, we see that there's a square, which means there are two solutions for this equation. Now, which one is valid? Well, if you think a moment, the answer should be pretty clear. If after the collision, the velocity of the first ball is 6 meters per second, that would mean it would increase its velocity, which doesn't make sense. So, the final velocity of the first ball must be equal to 2, and the final velocity of the second ball must be equal to 6. Let's see it in action. As you can see, the simulation matches up with our calculations. Now, how does this cover physics? We see we saw perfect elastic collisions, which means that collisions transfer kinetic energy perfectly. We saw the conservation of momentum, and then we saw how to use the conservation of momentum and conservation of kinetic energy to calculate the final velocity. Thank you all so much for watching.